Okay, so kind of where we ended up at the last lecture was this concept of impulse response, right? Which meant that, you know, we showed that if I knew what the response of a linear system was to the delta function, if I put that through my system and I got out some new signal, this is the unit impulse, or the delta function. This is the impulse response. And I wanted to know what would happen if I put an arbitrary signal into the system and got its arbitrary output. We showed that this output was what was called the convolution of the input with the impulse response. And that convolution was defined as this kind of complicated formula. And to make this, you know, proper, this system in the first place has to be linear and time invariant, right? Those properties that, you know, if I sum up two inputs to the system, I get the summed outputs, for example, and if I shift the input, I get the shifted output. Those are critical to make this whole thing work, right? If I don't have linearity and time invariance, then I have no guarantees about what the system might do to an arbitrary input signal, okay? So what I want to talk about kind of throughout today is exactly what is this convolution sum doing? What does it mean? Think about kind of different ways to interpret it, and then think about explicitly how to compute it for different signals, and then talk about just some properties of when I connect signals like this together, or systems like this together, I'm sorry. Okay, so like I said, this is really exciting. This basically says that all I need to know about the system is its impulse response. Then I can compute the output for any arbitrary input, okay? So let's look at a single system in a bunch of different ways. So let's say consider this LTI system. And so you're going to take my word for it that this system is in fact LTI. So one of the homework problems, for example, is to take a system and prove whether or not it's linear and time invariant. This one is linear and time invariant, okay? And so then I want to know what is the response to this signal here. So basically these are like 3 impulses of height 1. Okay? And so there are many ways that we can answer this question, right? So the first way is totally direct, right? So if I didn't know anything about impulse response, I didn't know anything about, you know, convolution, what I would have to do would be basically to kind of grind through this problem, right? I would say, okay, well, you know, y of -1, I would feed it into the formula. I'd say, well, y of -1 is x at -1, then I need to know x at -2, x at -3, all those things are 0, right? So I could kind of immediately say that all this stuff was 0 for all these negative numbers. Y of 0, I would say, was x of 1, and then this is x of -1. I don't need to know this stuff afterwards. Y of 1 would be x of 1 minus 2 times x of 0, which would be -1. Y of 2 would be x of 2 minus 2x of 1 plus 3x of 0, which gives me 2. Y of 3 would be x of 3, which is now, again, I've gotten off the signal on the other side, so this is 0. Then I have minus 2 plus 3 equals 1. And y of 4 is, x of 4 is 0, x of 3 is 0, 3 times x of 2 is 3, right? So I end up with basically a list of numbers. And so one thing that is going to make life a little bit easier is to represent, you know, these, like I could also more easily represent this input signal like this, 1, 1, 1, and I would use kind of like this little double underline to remind myself that that is where x of 0 is, right? So this double underline means, you know, n equals 0, kind of as a shorthand. And so my shorthand output for y would be 1, minus 1, 2, 1, 3. And it would start right here. And the same way, the impulse response of the system, as we're going to talk about in a second, can be written in a similar way. Okay? But I guess we don't know what the impulse response is yet, technically. Okay, so this is like, again, you would never do it this way in practice, but this is like the dumbest thing that you could do if you didn't know anything other than the formula for the system. Okay, so let's think about explicitly using the convolution sum. And what I mean by that is that, I've given you this formula that says that what I do is I have to figure out whatever this means, right? So for that, I need to know what is the impulse response, right? So what is the impulse response? Well, again, I need to go back to my formula and figure out what the impulse response is, right? I mean, right now, there's no other way to do it. So what I would say is, okay, my delta n is basically, just like this, right? Nothing else is non-zero. And so what I could figure out is that my h at all the negative values is 0. My h at 0 is going to be 1. My h at 1 is going to be 0 minus 2 is negative 2. My h at 2 is going to be 0 minus 0 plus 3 is 3. My h at 3 is going to be 0 and 0, 0, 0. Right? So I basically only get 3 numbers for my impulse response. And, because I am a professional, I know that if I look at these numbers here, these coefficients on the original system, basically I can kind of just read off the impulse response, right? 1 minus 2, 3 is the same as this 1 minus 2, 3 here, right? And so all you're kind of doing is you're writing down what are the coefficients on each of the delayed versions of the signal. So it's not like when I ask you for the impulse response of some system, you have to go through and churn it out. You can usually read it off from the form of the system, okay? All right, so now we know what the impulse response is, and if I'm just going to kind of write down what that looks like as a series of sticks, it looks like this, right? I have 1, minus 2, 3. This occurs at 1. This occurs at 2. And just to comment on the homework and the exams when you're writing things, remember that, to make it 100% unambiguous for me and the graders, you have to make sure that you mark down, what are the heights of the sticks and what are the positions of the sticks, right? Don't assume that everything is automatically height 1 and that these things are unit steps apart. That may not always be true, right? So just be conservative and careful about how you label stuff. Okay, so now let's look at what does this convolution sum mean, okay? Well, in this case, I have 3 values of x that are non-zero at positions 0, 1, and 2, right? Just a reminder, my original x looks like this, right? And so let's write out what does this sum actually mean. Well, it tells me that y of n is, if I kind of write out the interpretation of this, knowing that only these 3 values are not equal to 0, what I'd have is x of 0 times h of n plus x of 1 times h of n minus 1 plus x of 2 times h of n minus 2. Right? That's like saying that what I'm doing is I'm weighting these delayed versions of the impulse response by the coefficients of the input signal, right? And so what I can think of is saying, okay, that's like saying I take the original impulse response, which looks like this. This is going to be the first term. Then I take a delayed version of that. I'm going to have to kind of line these up to make sure I don't screw it up. And then I take a delayed version of that again. And so if I add these things up, I can basically add up corresponding sticks, right? I can say that I get, well, in the first case, the only stick I'm adding up is the first one, so I get 1. In this case, I get -2 plus 1 is -1. In this case, I get 3 plus -2 plus 1 is +2. Then I get 0 plus 3 plus -2 is back to 1, and 0 plus 0 plus 3 is 3. And so hopefully, I got the same thing that I started with, right? 1 minus 1, 2, 1, 3. And if I wanted to be a little bit less space-consuming on my paper, I could also kind of think about this as saying, okay, I take the impulse response, which is 1 minus 2, 3, right? This is the impulse response that starts at 0. Then if I were to shift it over by 1, I would have an impulse response that's still 1 minus 2, 3. That one now starts at n equals 1, right? So this would be the way I'd represent the shifted h by 1 unit. And then I could also shift the h by 1 more unit. Oh, sorry. You're right. I screwed this up. Like this, right? Yes. Good point. Right. So here I need to make sure I keep track of where the 0 element is. And so then if I add these things up, keeping the 0 element in one place, what I get is the right thing again. 1 minus 1, 2, 1, 3, with a 0 element here, right? And so, you know, in practice, that's probably easier than drawing the sticks, right? And so on your homework, if you want to kind of do this for the intermediate steps and then show me both this and this as the final picture, that's okay. You don't have to do the total stick figures all the way through if you don't want to. Okay, so again, that's not so bad, but it's still tedious, right? We would not actually want to kind of add up a zillion shifted copies of the impulse response every time we had a new input signal, right? And so that leads us to this kind of more graphical / mechanical method of doing convolution, which is the kind of flip and slide way of doing it. And so I'm not sure what the real name for this is, but I guess I would call it, you know, flip and slide one signal. And so what I mean by that is, let's again look at the convolution sum, okay? You know, another way of thinking about this is the following. So let's take my x of k, and I'm going to keep drawing the stick figures like this because I think this is easier than using the rows of numbers for the moment. So here, this is my x of k as a function of k, right? Well, what is h of n minus k? Well, remember that when we talked about transforming a signal, so here, k is like my dependent variable and n is like a constant, right? And so remember that there's this order that you have to do the steps in, right? And so what is going to be h of n minus k? It's going to look like basically this. It's going to look like the, so let's remember what h of k looks like. So h of k by itself looks like this. 1 minus 2, 3. Okay. So h of minus k, for example, looks like this thing reflected across the axis. And so h of minus k looks like the mirror image of h of k. So as a function of k, this is like h of minus k. And then h of n minus k looks like this signal slid to the left, slid to the right by n units. So h of n minus k basically is saying, take what used to be 0 here and move it over to n. And so in a generic way, h of n minus k looks like this, where what used to be 0 will begin at n. And then this number is n minus 1, and this number is n minus 2. And so what this convolution sum is telling me is that to compute the convolution, what I can do is I can find out this signal as a function of k, find out this signal as a function of k, multiply corresponding entries up and sum them up together, and that gives me one value of y. Okay? And so if I was going to do that, I think it's probably easier to show you with my little MATLAB demo than it is to do it on paper. So I was thanking my younger self yesterday because I wrote up a little conv demo long ago. So the idea is, let's suppose I put in my workspace variable, or let's suppose I put in a variable. So here's my x was 1, 1, 1, and my y is 1, negative 2, 3. My impulse response, right? And so again, this is already kind of what we know. I'm sorry that the maybe I should make sure that you can see what the left hand guys look like, right? And so again, nothing new has changed here, right? My impulse response is still 1, minus 2, 3. My output, I can see, is the same thing I got before in different ways. 1, minus 1, 2, 1, 3, right? So how does the convolution work? What's going to happen is you're going to see that this h is going to flip around, and then I'm going to start to kind of click it across the x, and at each point I kind of sum up the corresponding entries and add them up. So let's watch that work. So here's the flipped version. Then I get one entry here, I click the signal over by 1, I add the corresponding entries up, I click it over by 2, I click it over by 3, I click it over by 4, and by the time I click it over by 5, the signal has already kind of left, you know, any overlap with x, right? So let's watch that again. So basically, again, this kind of mirrors the same, I mean, in some sense you're not getting anything for free. You're doing the same computations that you had to do originally, but in some sense I think it's a little bit, well, I don't know if it's easier, but certainly a different way of imagining what's happening to the signal, right? This flip and shift. And so, again, in the beginning there's little overlap. Then I slowly overlap with more of the signal until I fully overlap the signal. And then the impulse response starts to move off to the right-hand side, and I leave the signal, right? And so I'm really doing the same calculations that I was doing in the previous method, the one where I'm basically just adding up shifted versions of the impulse response. But, you know, it's a little bit more of a mechanical way of doing things. This flip and shift and run across and add up, you know, and hopefully this is not the first time you've seen this if you already took a continuous time signals course. Usually when we teach you about convolution, the first thing we teach you is about how to do discrete time convolution, and then we talk about continuous time convolution, which is a little bit more messy with integrals and overlap and stuff like that. Luckily, we're not going to do any of that in this class, right? We're just going to stick with the discrete time version. Okay, so let me pause and ask. Any questions about this? Yes? Don't we usually do shift first and then flip? That's a good question. So let's go back and think about that. So it's important to convince yourself why h of n minus k looks like this, okay? And so let's think about that. So let's suppose as a function of k, I want to consider h of n minus k, where this is like a constant for the purposes of the discussion. A different way of writing this is just like h of k minus k plus n, right? And so if I think about, if I have some h of k as a function of k, you're right. I told you that when you do these kinds of things, you should shift first and then flip, right? So if I'm really doing this right, what I should do is do this shift first, right? That's like saying that I delay this by negative n units, right? So if I have a positive n here, that means that my new h has to look like this, where this is negative n plus 1, negative n plus 2, right? Because this is I'm thinking about n here as a positive number. If this is a positive number, that means that I'm delaying it, you know, back into time instead of pushing it forward in time, right? And then when I flip that around, so this is like h of k plus n. And then if I flip it, I get what I promised you I would, which is this. n minus 1, n minus 2. This is h of minus k plus n. Right? And so, yes, if I was doing it in the proper order, this is the way I should do it, right? But I get the same thing. Other questions? It's a good thing you brought that up because I thought of it as I was doing it that I should really be doing this in the other way, but yes. So I think that the reason I did it the other way is that, usually what you do is you rotate H first to kind of be in the 0 position, and then you slide it back and forth. And so it's a little bit easier in this case to flip it first and then shift it, but you have to know that you're shifting it in the opposite direction from what this sign of this guy is, right? Yeah?
When we have an impulse response that will have an effect like before the signal starts, does it still apply to, we'll still use the same?
Right, so the question is, can we still use the same thing when there's an impulse response beyond 0 on the left-hand side, right? So if I have negative values, like h of -1, h of -2. The answer is yes, the same idea applies. That would mean, as we're going to talk about in a second, that it turns out that an impulse response that looks like that means a system that is not causal, right? It means it's looking forward into the future for values of x. So we don't usually like systems like that, but the same flip and shift computation method does apply. And that's where it's really important to keep track of your 0 element. I'm going to do some examples of that in just a second. In some sense, we can do an example of that now, just to be totally secure in our understanding. So let's think about, let's see if I've got a different example here. I guess I can do it on the fly. So let's suppose that I have x of n is something like this. So x here is starting early. And let's suppose my h of n is something like this, where it has some values for negative values, okay? So here, it's really important to kind of keep track of what the right position of the answer for y is, right? So what I would do is I would say, okay, here is my x. The first thing that I would do is kind of draw things as a function of k, right? And I'm going to draw this a little bit bigger because I realize this is too small. Okay, so this is like x of k. And now I'm going to look at h of minus k, right? That's like this. And I know that when things are lined up like this, that is the answer for the n equals 0 position of the output, right? So when things are like this, what I would do is I would say, okay, I look at the product of these two things is -1, product of these two things is +1, so I get 0. So I know that my initial output for y at n equals 0 is 0, right? Now normally I would kind of click my way through and compute the rest. So I could do that. I could say, okay, now I click this one unit over, I would get an overlap that would look like, 1, 1. So I'd have an overlap like this. And then as I move off to the right, I would have lost any overlap, and so all this stuff would be 0. But in this case, I also have to think about what happens when I move this signal over to the left, and to the left some more, right? That means that I may get some y values that are non-zero for negative n. So if I move over to the left one, then I have an overlap again where both these guys cancel each other out, so I would get this. And if I move it over to the left one more, I would get another signal like this, right? So I would have a result that would look a little bit different, right? And so in this case, it's kind of important to realize that you can't just stop for the right-hand side part of the signal. You have to do the whole signal, and you have to remember, where does my 0 element land, okay? And so I'm going to show you a faster way of doing convolution that kind of makes this thinking a little bit easier. So this is what I have seen called the convolution array method. I call this the WASI method because that's where I learned it from. So the convolution array method is super easy, right? What you do is you take the elements of x and the elements of h, and you make a table, right? And so let's take the example that we had before. X was 1, 1, 1. H was 1, -2, 3. And then what I'm going to do is I'm going to fill this table up with products of values of x and h, right? So 1 times 1 is 1, 1 times 1 is 1, -2 times 1 is -2, and then I get this. Then what I do is I look at the diagonals of this table, and I add up corresponding values, right? And so here I get, 1, -1, 2, 1, 3, right? Very easy. And how do I know what is the 0 element of the result? Well, what I do is I underline the 0 element of the input and the 0 element of the impulse response, and where those two things cross is the 0 element of the output. Wherever that double underscore lands is where I put my n equals 0 for y. And so that tells me I know that this is my answer, right? So again, really clean, really easy. And let's take the example I just did before. So the example I just did before was this guy. So here, how would I handle this? I would say, okay, my x has got values 1, minus 1, 1. My h has got values 1, 1. The 0 value is this here, and the 0 value is this here, right? Now I multiply these things together. I make my array. I mark where do these things cross, and then I get 1, 0, 0, 1, where the 0 value is the second 0, right? And hopefully, if I compare it to this is what I got, right? 1, 0, 0, 1, where the 0, the second 0, falls at the 0, right? And so, you know, I think we can all agree that that is much easier than any of the previous methods I showed you so far, right? You just make this table, you sum up some numbers, you never go wrong, right? So because this is an easy and important method, let me ask, are there any questions about this? Okay, so when you have two finite length signals, finite impulse response, finite length input signal, then this is, you know, perfectly reasonable way to do convolution. So unless I tell you otherwise, this is fine for you guys to use. The catch is that you can't use this for every input signal, specifically the ones that are infinitely long, right? So life is not so easy when we have a certain situation like this, right? So let's suppose that just to belabor the point, let me do one more example, just because I have it in my notes here. So let's take x. Let's suppose it looks like this. Minus 2, minus 3, and let's take h to be minus 1, 1, 1. Okay? And so convolution array method would tell me I take x, I take h, I number the values, so I have minus 3, minus 2, 2, 1. I take h, I get minus 1, 1, 1. 0 element is here, 0 element is here. I start multiplying stuff together, so I get 3, 2, minus 2, minus 1, 3, minus 3, minus 2, 2, 1, minus 3, minus 2, 2, 1. 0 element is going to be over here. I make my diagonals, I add things up, and I get 3, minus 1, minus 7, minus 1, 3, 1. And the 0 element turns out to be this guy. Right? Very fast, very easy, right? Okay. So let's talk about when life is harder, right? So we're not usually, I mean, it is true that, you know, a lot of times we deal with what are called finite impulse response systems, ones for which h of n is non-zero only for a finite number of values. And often we do have, you know, finite inputs also, but a lot of times we're looking at inputs that are infinitely long, okay? And so in that case, we need to be able to understand how to still do convolution when we've got more complicated input signals. And so here's an example. Let's suppose that I give you something that's actually more symbolic, right? X of n is alpha to the n u of n, where alpha is in 0 to 1, and h of n is u of n, right? So suddenly we've kind of stepped it up a little bit. So now instead of having just numbers, like solid numbers to work with, I've got symbols, okay? So let's see if we can kind of unpack this. First of all, it's good to visualize what do these signals actually mean, right? So we know that the impulse response is easy. That's just the step function. So nothing happening, then the step turns on. Dot, dot, dot. What does the input look like? The input, again, since it's multiplied by the step function, that means that nothing can be happening before 0. What happens at 0? At 0, the signal starts happening, and at 0, the value of this is alpha to the 0. So that is going to be 1, no matter what alpha is. At n equals 1, I'm going to have alpha to the 1 power, and since alpha is less than 1, that means I'm going to get a slightly shorter stick. At n equals 2, I'm going to get alpha squared. Again, since alpha is less than 1, I'm going to get a slightly smaller value. And so kind of what I get is this exponentially decaying input signal. But this exponential decay goes on forever, right? For any value of n, no matter how large, I'm still going to get a little non-zero value of x. And so I'm forced to consider what happens for infinitely large values of n for y, okay? And so let's think about what is going to be the convolution between these two things. Well, one nice thing about convolution, which I'm going to show you in a second, is that it doesn't matter which order I flip and shift the signal. It doesn't matter which signal I choose to do the flip and the shift. I can either choose x or I can choose h, right? And so in this case, it's going to be a little bit easier for me to choose h, right? So what I'm going to do is I'm going to flip h across the y-axis, right? And so again, I can see that for n less than 0, that means I'm going to be shifting h this way. Nothing is going to be happening because there's going to be no overlap. When I'm right at 0, I get 1 times 1, right? So I'm going to make a little table like this. Y of 0 is 1 times 1, which is 1. Y of 1 is what I get when I click this 1 unit over. So now I'm going to have this overlap. And I'm going to get 1 plus alpha. Then I'm going to get a little bit more when I click it over 1 more unit. I'm going to get 1 plus alpha squared. And so now I see there's a pattern, right? And so if I were to write down my pattern, I also say that, by the way, y of -1 is 0, and all this stuff is 0 up this way. So my pattern would be basically saying that y of n looks like, it's 0 for n less than 0. And for n greater than 0, it looks like the sum from k equals 0 to n of alpha to the k. Again, let's unpack this a little bit. So that means that this is just saying, like, when n equals 2, I get 1 plus alpha squared. That's what I got before. And a more this is kind of like this kind of cases way of writing things. Equivalent way of writing this is just the following, which is to say that I have this thing times the step function. Right? In this way, I've kind of compactly written what happens. And this makes it really clear that the output is non-zero when n is less than 0. Okay? And so now the next question is, can we do better than this even? Right? And you should remember, now there's this formula bubbling up from your business of calculus brain that says that I can take this finite series and make it simpler, right? And so this guy turns out to have a special form. And so let's just take a sidebar for a second and remind ourselves, remember, when I am confronted with a sum that looks like this, so if alpha is between 0 and 1, when I see this, I can turn this into 1 over 1 minus alpha. And let's think about why that's true. Again, what does the left-hand side look like? The left-hand side looks like, this infinite sum. And what happens when I multiply this by the denominator here, 1 minus alpha? Well, what I get is, I get this whole thing minus alpha times the same thing. So I get minus alpha times 1, minus alpha times alpha, and so on. And so I can see that when I subtract this from that, I get 1, right? So the formula checks out, right? Makes sense. And so I can use this formula to figure out what should this thing be. Okay, if I want to only sum up to n, one way to think about this is it's like saying, what if I were to sum up to infinity and then subtract off the sum that starts at n plus 1 and goes to infinity? That's like saying, just give me the first n plus 1 terms of the sequence. And I already know this is 1 over 1 minus alpha. And now this thing is going to be the same as saying, well, what if I took an alpha to the n plus 1 power out of this sum in the first place? I'd get the same sum. So what I have here is an alpha to the n plus 1 over the same sum. And then what I get as a result is 1 minus alpha to the n plus 1 over 1 minus alpha. Okay. So these are kind of good formulas. Just like usual, when you have an exam in this class, I'm going to give you a formula, or I'm going to let you write your formula sheet that reminds you of, some things that you need to remember. This would be a good thing to put on your crypt sheet just to have it in your mind. But this is, you can see that this is always not so hard to rederive in case you forget exactly how it works. Just kind of start from this principle, okay? So let's go back to our actual problem here. Our problem was exactly this, where I have exactly this sum, and so I can substitute my formula and say this is actually equal to 1 minus alpha to the n plus 1 over 1 minus alpha times u of n. Okay. And so, actually, let's think about just for a second, what does that mean? Like, what should that look like, right? So let's go back to our picture of the signals. So one way to think about this is that what I'm doing is, as I'm basically making a cumulative sum of the values of x, right? So in the beginning, I'm adding relatively larger sticks to my sum. And so the sum will grow faster in the beginning. And then as I move my h along the signal, the next little bit that I add from the original x is pretty small, and it gets smaller and smaller. So it's kind of like I'm going to reach a point of diminishing returns. And so the output signal, if I were to kind of sketch it, would look like this, right? It would look like, in the beginning, I have the first stick, which is 1. Then I add some more. Then I add some more. And eventually, I'm going to kind of like taper off, right? And there's going to be kind of an asymptote that I never quite reach. And I can kind of look and see, well, what happens if I take y and I plug in, as n gets larger and larger, plug in n equals infinity here. That means the numerator is 1, the denominator is 1 minus alpha, and what I get is, this is my asymptote, right? And since alpha is some number that's smaller than 1, this is going to be asymptotically something that's bigger than 1. So for example, if alpha equals 1/2, then I plug in this and I get, it goes up to 2 eventually. That's like saying if I add up 1 plus 1/2 plus 1/4 plus 1/8 and so on, eventually I get to 2 in the limit, right? Okay. So any questions about this example? One thing I want to do, though, is also show you, if you don't, so this is a graphical kind of way of doing it, right? I kind of added up a bunch of numbers, I saw the pattern, I figured out what I had to do. In theory, I should be able to get to the same answer just by the raw convolution sum, right? So let's think about that for a second. So what if I told you, you have to do it this way, right? You have to use the convolution sum. And this is something you should kind of get used to doing. So let's plug in, what do I know for these signals, right? I know that x of k is going to be alpha to the k u of k. H of n minus k is u of n minus k, right? So one way to think about this is these step functions, it's kind of good to think about what do these step functions look like and what does their product look like, right? So now this is a world where everything is a function of k, right? And so this u of k, right, if I think about it, when k is negative, the step function is 0, right? So this is like a step function that doesn't turn on until k equals 0. And so that means that I can immediately remove this guy entirely and kind of turn it into a sum that starts at 0, because I know that nothing can be happening before 0. Alpha of the k, u of n minus k. Okay. Now I look at this and I say, well, this is like a step function. What does u of n minus k look like? Well, this is just like taking the step function, flipping it, and shifting it over to be n units over. So this looks like a function that looks like this, where it turns off at k equals n, right? And so here, what I can do is I can remove this and say this looks like a function that, I replace this infinity by something that stops at n. Okay. But I have to be a little bit careful, right? Because if n is less than 0, then I've already kind of, my k here basically is starting at 0, right? So if my shifted impulse response is only non-zero over here, I'm going to get 0, right? So n has to be greater or equal than 0 for this sum to make sense. Otherwise, this sum is like going up to -5, right? So that's why I can make this substitution here, kind of saying that this here is equal to 1 for k less than or equal to n. And so I need to make sure that the sum, that the n here doesn't dip below my lower index of the sum. And so that's why it's important to remember that I have this step function hanging around, right? So you can kind of, when you see this kind of thing, immediately make a shortcut to sum from k equals 0 to n times the step function and then whatever's inside. So I can get rid of those step functions relatively easily by changing the limits on the sum. Okay? And this is where I got to before. Then I have to simplify this sum using my formula. Okay, so questions or comments about that? Okay, so you're going to see some problems on the homework that are along those lines, right? So some simple problems that you can solve with the convolution array, and a couple harder problems you have to actually solve by manipulating the formulas, right? I would prefer you to get comfortable with manipulating the formula, right? I think this here, once you know how to do it, is a little more straightforward. You can always add up a few values if you need to kind of confirm to yourself you're doing the right thing. But I think this is probably the easiest way to do it, as opposed to sketching and shifting and adding stuff. Okay. All right. So now what I want to kind of talk about is just a couple of little cleanup things, including what are the properties of LTI systems as I combine them, okay? Because a real-world system is usually composed of lots of little subsystems put together either in series or in parallel. So we need to know how we analyze those systems, right? We don't want to have to compute, even if we're using, some nice convolution method, we don't have to kind of compute the convolution from one impulse response and then the next one, and the next one. That would be a pain, right? We want to have kind of like an effective impulse response for the entire system, okay? All right, so let's just talk about properties of LTI systems. Which are really, it's kind of really a different way of saying properties of how convolution behaves, okay? All right, so the first thing, which I've kind of said a couple times now, just to have it in writing, is that an LTI system is entirely determined by its impulse response. Right? That kind of underlies everything I talked about so far, which is basically that as long as I know h of n, all I have to do is convolve x with h, and I know how the system acts for any input signal, right? This is not true for non-LTI systems. to be clear. So for example, here's a system that is not LTI. In particular, it's not time invariant, okay? And so what happens if I were to put the delta function into the system? Well, if I put the delta function in, what I get is, well, at 0, I get x of 0, which is 1, times 0, which is 0, so I get nothing. When n is not equal to 0, then the delta function is always 0 everywhere else. And so when I put the delta function into the system, I get exactly 0, right? Now, if I said, okay, if I treated this like an LTI system and said this was the impulse response was 0, then I would never get any non-zero output for any other input signal. But this system will do things to non-delta function signals that are not 0, right? So I can't just say that by knowing that 0 comes out, I know everything about this system, right? And this, in some sense, is the power of LTI in the first place, is that I don't have to figure out, okay, well, now it happens with this other signal, right? How would I analyze an arbitrary signal? I have to crank it through the system, right? Okay. So commutative property. Oh, before I go on to this, let me just say one thing. So it is true that if I know the impulse response, I know everything about the system, right? It is also true that if I know the response to some special input, if I can write any other input in terms of that special input, then in fact that thing characterizes the system too. So for example, I could, for example, put the step function into a system, find out what the step response is, and as long as I know how to take my arbitrary input and decompose it in terms of step functions, then I could characterize things with the step response, right? In a similar way to how I do it with the impulse response. And so that's kind of an important and useful fact to know. So for example, in a real-world scenario, right, what does the impulse response mean? So suppose I'm trying to, so a common thing to do for acoustics, right, and you can say more, right, is that you're in a concert hall, right, and so what would you do if you wanted to measure the impulse response acoustically? That would mean basically like firing off a shot, something that is like an instantaneous bang, And again, you want to make it as loud as possible so that you hear the reverberations, and that's your impulse response, right? But in some situations, it may be hard to get an input signal that is really loud for an instant and then turns off, right? So instead, what I could do is I could provide, for example, let's say I provide a system that turns on and stays on, like that's a step function, right? That may be an easier signal to physically produce for the system. And then I could measure what I get, and I could turn that into the impulse response later, right? Or I could maybe measure the response to something like a pulse of sound, right? Turn it on, turn it off. So the mechanics of how you would use the responses to these other special input signals to produce the response to any signal is the subject of one of the advanced homework problems, right? So if you look at, so again, keep in mind that on the homework there are some starred problems that the 4,000 level class doesn't have to do, but you should at least read them to find out what I'm asking, right? And you should, in theory, be able to solve those problems yourself if you wanted to. So one of them is basically saying, let's suppose we take some other special signal and figure out how would we calculate the response for an arbitrary input, knowing what the system did to the special signal, right? So that's kind of interesting to think about. So all I want to say is that this is not like an if and only if. Like it's not like I only can handle things if I know what the impulse response is. I can do things when I have responses to other signals too. Okay, so commutative property. Commutative property basically says that if I were to interchange the order of the signals when I convolve them, I get the same answer, right? And so to be clear, I defined this convolution as the following. This sum, right? And the interpretation of this is that I keep x the way it is, and I flip h, and I run h across the signal, right? And like I told you earlier, I don't have to flip h. I can flip x instead and run it across h. Let's show why that's true. I can do that by basically a simple change of variables. What I would say is, let's let this thing equal m. So that's like saying m equals n minus k. And that means that k is n minus m. And if k goes from minus infinity to infinity, that means that m also goes from minus infinity to infinity. So by a change of variables, I would say that I have from m equals minus infinity to infinity of x of, let's see. So I said that k was n minus m, and n minus k was this, right? And that's the same thing as if I were to interchange the signal order, right? And so like I said, when you're doing homeworks and stuff, you may find that it is easier to flip one thing than flip the other thing. So don't worry about which one you flip. Okay. Next one is the distributive property. That basically says that if I have a kind of a chained convolution, or I'm sorry, maybe more better to say it like this. Suppose I have to go through two systems in parallel. That this is the same as this. And all this stuff really kind of falls out of the LTI, properties of the system. To make this a little bit more visual, what this means is that if I have a signal that goes through two pieces, and then I add those pieces up later to get y, an equivalent system is this. Or a slightly more useful way of thinking about this, since I can interchange the x's and the h's, is saying that if I add up two signals and I put them through the system, that what I get out is, actually maybe a better way to think of it. I guess I already knew this was true from linearity, so let me scratch that. This is basically more like saying that what happens when I when I put these systems in parallel. So again, like my graphic equalizer, this is like saying that I can get the effective response of my graphic equalizer by creating a combined impulse response from all that stuff. Okay. And that can be used to kind of break up convolutions that might otherwise be a pain to do. Okay. All right. Next one is the associative property. I forget whether I'm numbering these. Okay. This basically says that if I have something like this, that I can kind of put the parentheses wherever I want. I could basically say that I can move these parentheses around. Or I could remove the parentheses altogether. This is really important in terms of the way that systems are composed, right? So for example, what this is saying is that if I put a signal through a system with one impulse response, and I put it through some other system and I get my result, that I could equivalently put this through a single system whose impulse response is the convolution of these two guys. And if I combine this with the commutative property, I could say, okay, well, I could also interchange the order of these two guys, because I would get the same answer. And as a result, I could take this apart again and say that it doesn't matter what order I put the systems in, right? I can switch the systems themselves, right? And so that's an important result. That says, number one, that I can effectively combine all my LTI systems into one blob, and number two, that I can put the systems in any order that I want, and I should get the same answer, right? And that's a little bit maybe counterintuitive, because that's definitely not true for nonlinear systems, right? So for example, let's consider something like this, where I have a system where first I multiply by 2, and then I square the result, okay? So here, that's like saying that I multiply the system by 2, signal by 2, and I square the result. What I would get out would be 4x squared. Whereas if I were to square the signal first, then multiply by 2, what I would get would be 2x squared, right? So here, this is a situation where interchanging these two blocks doesn't give me the same answer, and the reason is that this x squared block is not linear, right? So I can't use my LTI properties, okay? And so that's kind of an important thing to remember, is again, this system interchangeability only applies to LTI systems. Okay. I think that one more thing is causality. Okay, so there was a question earlier about, is it possible, or what happens when the impulse response of the system is 0 for values less than 0? Okay, so let's remember what causality means, right? So kind of a slangy way of saying it is that y of n doesn't depend on x of n plus k for k greater than 0, right? That's like saying that if I want to know y of 3, I'm not looking into the future to get x of 5, right? And so again, if I write my convolution sum, and this time I'm going to write it in the way where I'm putting the h first. So kind of looking at this and thinking about how that applies to this formula, that's like saying that, if k is negative here, right? So if k is negative here, that means I'm looking into the future of x. And so that means that if I have a causal system, that the corresponding impulse response value has to be 0, right? I have to be multiplying future values of x with 0 for this to work. And so that means that for a causal system, h of k has to equal 0 for k less than 0, right? That means that my impulse response has to look like something that is 0, and then it can start here if I want it to. But I can't look into the future. That means that all these values have to be 0, okay? And so that's why a lot of times our impulse responses look like something times the step function, right? They don't start before 0 because we like to have causal systems, okay? I mean, another way of thinking about this is that the impulse response has to be 0 before the impulse occurs, right? So the system cannot be doing stuff before it sees the impulse, right? I mean, the impulse response occurs at 0. The system can't do anything before 0, right? That kind of stands to reason, okay? Okay. So one thing I mentioned, right, is I mentioned in passing the step response. So remember that the step function, right, we talked about this last time, is that since the step function is related to the delta function as follows, right? That's like saying that I take the step function and I shift it over by 1, and I subtract them, I get the delta function, right? Now, if I put both sides of this into the system, what I get is, here I get the impulse response, and here I get what I'm going to call the step response. And by time invariance and linearity, I get this. So this here is what's called the step response. That's like saying I take the system and I apply it to the unit step function. Okay. Or a different way of saying things is that since the unit step looks like the sum of the delta functions up to a certain point, that my step response is equivalently the sum of values of the impulse response up to a certain point. So all this is basically saying that if I know the delta function, if I know this impulse response, I can get the step response and vice versa. And so for the purposes of analysis, if I know what the step response is, I can go back and compute the impulse response and thus compute the response to anything. So basically, the step response also characterizes the LTI system. Okay. so again, the reason I'm giving you all these properties is so it simplifies your life in cases where you have to compute what may look like tricky parallel or serial combinations of systems, right? So the best thing, well, not the best thing, but it's often useful to say, okay, before I just kind of brute force my way through a lot of convolutions, I should think about, can I take pieces of this system and combine them in ways that make my life easier, right? So for example, let's suppose that I had, some problem where I had some sort of like, crazy signal, whatever, and I put it through a system whose impulse response is the step function, and then I put it through a system whose impulse response is this very simple guy here, 1 minus 1. Right, so to do this, what I have to do is first I have to convolve this with that, then I have to convolve that result with this. Instead, I could observe that here, the convolution of these two things is really easy, right? So if I flip this guy and shift it across, I can see that my effective system is basically, well, it's nothing happening before 0. At 0, I have an overlap of 1. And then when I shift the signal across this way, I have a +1 times a -1. So fundamentally, all these guys get canceled out. So the effective system is just the identity function, right? That means that whatever comes in is exactly what comes out, right? No need to compute anything. And so it's kind of worth thinking about, can I simplify the system to be easier, right? So you may see that there are going to be some, like there may be an exam problem or something like that where you have to do some sort of convolution. Looks like a pain, but think about whether you can make it easier. Question? Why isn't there a negative? Well, because this is going on forever, right? So this is like the step function. Yeah. Yeah, if it's not going on forever, then you have to go back and deal with it. Okay. And so the last thing I kind of wanted to mention, just kind of in passing, is, and I think I said this once already, is that many kind of electrical and mechanical systems are described by differential equations. Right? So if I have kind of like a mass spring system or a RLC circuit or something like that, then I have some sort of a differential equation I have to solve. And so presumably you had a whole class on trying to solve differential equations and understanding where they came from in different scenarios. I'm not going to do all that again. But the discrete versions of these are called difference equations. And difference equations usually kind of look like, something like this. I've got some, I've got some number of output values, and that's equated to the sum of some number of input values. And these are called basically linear constant coefficient differential equation, or difference equations, right? And so, again, the way that you solve these things is the same kind of way that you solve differential equations, right? My solution is going to be basically something like a homogeneous solution. So I have to make my h's and my n's kind of straight here, plus a particular solution. And again, for the regular class, I'm not going to go into this too much. For the advanced class, I put a homework problem on solving difference equations by treating them like an LTI system, okay? So life is good when I only have basically one term over here. So when I basically have y of n equals the sum of some previous values of this, well, that's kind of like the systems that we've been talking about so far, and that's called a finite impulse response system. We're going to talk about that a lot in the future. So again, when I have something like this, this is basically what's called a finite impulse response system. And here, there's really nothing to solve necessarily, right? I mean, I use convolution to get the answer. Whereas once I start combining previous values of y, then I have to have this recursive solution to get the difference equation answer. And that's where you have to kind of go through the machinery of homogeneous solution, particular solution. Since this is not a class about differential equations, difference equations, I'm not going to go through this right now. But the mechanisms are the same. And as we're going to see, all the stuff that we've been talking about, convolution and the responses of LTI systems, can be greatly simplified with the tools of frequency domain analysis, Fourier transforms and Z transforms. So just generally transform methods, right? And so when it comes to needing to solve these kinds of things, hopefully at the end of your differential equations class, you found out that the Laplace transform was really the best way to solve those equations instead of trying to guess what might be the answer, right? The same thing is true for difference equations. Once we know the Z transform, life is very easy, right? So we may come back to talking about difference equations when you guys know the Z transform. Okay. All right. So I think that's where I'm going to stop for today. Are there any questions about anything? Okay. So give me 1 second while I shut down my guy here.